Hi, my name is Michael and I'm a Chem 121 PLF. Today I'm going to be guiding you through a heat capacity problem. So our problem is stated as how much heat energy is transferred to a 190 gram chunk of ice when heating from negative 12.2 degrees Celsius to a final temperature of 28.7 degrees Celsius. So when you approach this problem, you think, okay, we know that Q equals N times Cp times delta T. We got our final temperature, initial temperature, so we can just plug and chug. However, this one, there's a caveat. We cross a critical point, which is the freezing point of water, because H2O is frozen as ice. So there's something, we can't just go straight to the answer by doing 28.7 minus a negative 12.2 degrees Celsius. So in order to conceptualize this better, we need some equations, some constants for Cp of water when it's frozen and liquid, and also when it melts. And in order to conceptualize this, I'm going to go ahead and draw a graph. Our graph is going to be y-axis degrees Celsius, and our x-axis is going to be in joules. We start at negative 12 degrees, negative 12.2, and we go to the freezing point for the first part, and I'll say 0 is right here. So as the solid piece of ice goes to the freezing point, gains energy, we'll have one segment, and then we'll have another segment where the solid ice is becoming liquid ice, but the temperature is not changing, it's still 0 degrees Celsius. So the point probably right about there, and then once it's fully liquid and gaining energy up to our final temperature of 28.7, I'll say that point right there. So we'll have 3 line segments, and this is not to scale, this graph. This first line segment is going to be from negative 12.2 to the freezing point, and we'll call this one Q1. Alright, so we know that heat capacity problems involve an equation that's generalized to be N times Cp times delta T. Well, we don't know what the N value is yet because we just have a gram amount. So we'll do some dimensional analysis to calculate what the number of moles is for this piece of water when it's frozen. So we do 190 grams H2O, and it's solid. And we'll divide by the molar mass of water, which is 18.00 grams per mole. Grams cancel, sorry. And we're left with moles. 190 divided by 18.00, and we get 10.5556. All right, moles of H2O. So I'm going to hold on to some extra decimal places here just because I want a more accurate final answer. So N. All right, now we can start working with some equations. So for Q1, our equation is going to be N times Cp of solid water times delta T, final temperature minus initial temperature. All right. Heat capacity of solid water is 37.1. This kind of stuff isn't worth memorizing. I just write it down on a note card. Times degrees Celsius. Joules per mole times degrees Celsius. All right, and our delta T is our final temperature, 0 degrees Celsius, minus our initial temperature, 12.2. That's going to be 0 minus a negative 12.2 is a positive 12.2. All right, our units cancel, and we're left with joules, which is what we expect. So let's go ahead and compute this. Times 37.1 times 12.2, 4,777 and 0.675, and we'll round up to 6. And that's joules. All right, there's Q1. So for our second line segment, temperature is not changing, but we're undergoing a phase change. This critical point is solid water, and as we move to the right, we have some liquid water forming, and farther right we go, we have less solid water and more liquid water until we reach this critical point here where it's completely liquid water now. So this is going to require a different equation. I'm going to call this segment Q2. So Q2 is equal to N times delta H fusion of water, which is just water when it melts from solid to liquid completely solid, completely liquid. All right, so 6,010 joules per mole is the value for delta H fusion of water. So now we'll go ahead and plug in these values. Joules per mole are the units for delta H fusion of water. No temperature change. So we'll go ahead and compute this. Joules. All right, and our final line segment will be from 0 degrees Celsius to 28.7 final temperature degrees Celsius. And we'll use the initial equation that we used for Q1, which is NCP delta T. However, this heat capacity value, this constant, is different from the constant right here. So heat capacity of liquid water is 75.3 joules per mole divided by mole times degrees Celsius. Plug in those values. And final minus initial, 28.7 minus 0 is 28.7 degrees Celsius. Our units cancel, giving us joules. And we'll plug in those values, 10.6. 22,811.813, rounding. That is Q3. So we have 3 line segments, and as you can infer, this line segment I was referring to as Q3. So we have 3 values for energy that we computed as we've gone from our initial temperature to our final temperature. So we need to sum these up to get our Q total. Q total equals Q1 plus Q2 plus Q3, which equals 4,777.676 plus 63439.156 joules, and 22811.813 joules, and that equals, let's see, 22811.813 plus 63439.156 plus 4,777.676 equals 91,028.645. Now, if we go back to the beginning, we see that there's 3 significant figures in the problem for the temperature, both initial and final, and for our mass. So we know that our final answer should have some 3 sig figs. So now that we've held on to that extra data, we find out that we really just need a whole number and actually a little less. So I'm going to round up the decimal place 0.6 to the next nearest whole number, which is 9. And then we can convert this using dimensional analysis to kilojoules. So we know 1,000 joules equals 1 kilojoule. So I move the decimal place to the right 3 times, and that gives us 91.0 kilojoules. We can also use this value and convert to scientific notation if we would prefer. that's equal to 9.10 times 10 kilojoules. Q total. And that would be our final answer. Thank you for watching.